Okay, hello honors chem students. Just want to give you a quick little video here about some of the important aspects of today's learning that you have gone through. Talking about multiprotic acids. Multiprotic acids means indeed that there can be more than one proton. Here is an acid right here, and this is actually a multiprotic acid. This would be H2SO4, where this yellow sphere is the sulfur. The red is the oxygen, and you notice there's two whites. Those white molecule or spheres here would represent hydrogen ions. This is the model for what we call sulfuric acid, H2SO4. So acids can be either monoprotic, which means they only have one hydrogen, diprotic, which means they'd have two, or triprotic, which means they'd have three hydrogens that were allowed to ionize. So oxyacids are another example of multiprotic acids. We actually call them multi, meaning more than one proton to dissociate. However, most multiprotic acids are what we call oxyacids, and that's when you have oxygens attached. So this is actually phosphoric acid. This orange would be the phosphorus. You have 4 oxygens and you have 3 hydrogens in this molecule. So that is what we call a triprotic acid as well. Okay, so another important aspect is this idea about oxyacids, and this is the hypochlorous to perchloric acids series, is that if there are more oxygens, as you increase the amount of oxygens that can be in the molecule, the stronger the acid. So this perchloric acid here, which is, as we know, HCO4, that coming from the perchlorate ion. If we put an H in front of it, it's called perchloric acid. This would represent the H. And as we're looking at this, because of the electron density, because these are so highly electronegative, that makes this hydrogen-oxygen bond very weak compared to here, where you have the hydrogen-oxygen bond, but since there's only one oxygen, and here there's more oxygen, there's only one oxygen on this port, the electrons are more evenly distributed, so that hydrogen-oxygen bond is actually stronger than this hydrogen-oxygen bond. So what does that do? That makes this hydrogen easier to get kicked off and to dissociate. The more H's that will dissociate, the stronger the acid would be. So that's something to know about the oxygen series for oxyacids. The other thing that I want to kind of talk about, and I know you have these notes on your page, strong acids, you have complete ionization or what we call dissociation. In this class, I'll keep those two terms to be analogous. Just don't hold me to it when you go to a college class. There's a little bit of a difference, but you'll learn about that a little bit later. Examples of strong acids are like HCl, HNO3, H2SO4, known as hydrochloric, nitric, and sulfuric acid. There's also things that are strong bases, which will completely dissociate, and those would be like sodium hydroxide, potassium hydroxide. There are weak acids and weak bases where they do not completely dissociate. Most of the acid stays together, and that's what I was hoping you guys saw in the video that you watched. A weak acid will stay together and only a small portion of the hydrogen ion dissociates. So if we were to look at a beaker of HF, most of the molecules would stay together. It would be HF, and there would only be a small portion of hydrogen ions and fluoride ions. And the same thing with weak bases. They do not completely dissociate. Most of the bases stay together. And the common base that you should know, weak base, is called ammonia. All right. So the last piece I want to show you is just this little picture here when we're talking about what's happening when you're dissociating. So a strong acid, this is a beaker of what a strong acid would look like. Do you notice that the species has an H plus and an A minus? That means it's completely breaking up. It's a good conductor of electricity, okay, because there's many ions here in order for that to conduct the electricity. Compared to a weak acid here, notice how like right here and right here and right here, that's staying together. It's HB in this example. That represents a weak acid. Only a small portion completely dissociates. And you wouldn't even call it completely dissociating at all, only a small portion. So we call this a very small portion of a dissociation. Okay, we're going to learn more in the next lesson on the next day as far as what that really all means. Right now, all I want you guys to know is there's a difference between a strong acid and a weak acid. So in summary, I'm hoping that you're reading through all this. It's really important that you watch this video, okay, because it's also going to animate and show you on a molecular level what is the difference between a strong acid and a weak acid. Here are the pages that we had went over that they talk about. And this last one is again indicating what you should know about a strong acid and a weak acid. So if we look at the strong acid and we're just labeling this HA, it completely dissociates. So if we were looking at this in a beaker, there would be no HA together. It would all be H plus and A minus. A weak acid only partially dissociates. Only a small amount of H plus and A minus would be found in this beaker. And notice this is important. There is a difference in the arrows. The arrow drives almost one way. Sometimes in college you might even hear that it's very little going to the back, but that's not even, I mean, it's really, really pretty much will completely, almost like 99.999% of this acid will dissociate. Whereas here, it's more in an equilibrium position when you're talking about a weak acid. Those will be things then that we'll learn in the next lesson when we're talking about Ka values. So that's kind of like a KEQ, and that's coming in the next lesson tomorrow. Okay, so this should just help you for today. So you're going to want to go through and actually make sure you're doing this quick worksheet and that you also complete the daily quiz. Hope you guys have a great day.